Thank you. Oh, some more people. So thank you to Professor Kim. Thank you to Jang-Soo Kim that took care of me here for the first few days, and thanks to KAIST for having me here in Korea. It's my first time in Korea, even first time in Asia. So really happy to be here. So my first talk will be very combinatorial talk, a lot of bijections in it. So it's a joint work with Olivier Bernardi, who is now at Paris 11, and Bertrand Duplantier, who is CNRS affiliated to Lyon University, I think, in France also. So it's called Well-Label Path in the volume of a polytope. That will first talk about the polytope and then the path. So the polytope, we'll try to compute combinatorially the volume of a polytope, which has a very nice formula. And for this, we'll try to do it bijectively, and this will involve these and matchings, which are very known combinatorial objects. And in the end, we'll give a couple of applications of the bijections to permutation and enumeration. Let's see. So we'll first start by the motivation. So Bertrand Duplantier actually is a physicist. So he studied a polypeptide model, so it's some kind of molecule, if you want. So in a very rough model, you can describe it like here. So what is this model? Let's say it's attached here on the ground, and you have unit line segments, if you want, and they can move freely, okay? But they all attach and they're all of unit length. And so he tried to compute. I will not go into details of what he did because first I don't really understand it, but also in a particular case he was interested in computing the space of configurations, let's say, of this model, let's say. So what I mean is, if it's attached here, this one, as you can see easily, can have height at most 1 because it's attached to the ground. And so I'll just take care about the height. The rotation, I don't really care. Okay, we just see what heights are possible for the different points where the segments are attached. Okay, so this will have height between 0 and 1. The next one will have height between, which has to be at most 1 from the first one, of course, because it's attached by, etc., etc. So if we call this the different heights x0, x1, x2, x3, we'll have some inequalities. And plus, I want this to be bounded below by the xy plane, if you want. So all the coordinates that I described have to be positive. Okay. So what you get is some inequalities that I gave here that you can recognize. So x0 equals 0. Then all the xi's are positive, and the absolute value of the difference has to be smaller than 1 because they are the ends of a unit length segment. So this, as can be easily seen, is a polytope. It's bounded because by induction you will see that the xi has to be between 0 and I. It's by easy induction on this and the fact that it's positive. And so we like to compute the volume of this polytope. So when actually Bertrand Duplantier, who is at the origin of this problem, first computed it by multiple integrals, like classical formula for a volume, and he used complex analysis. It was quite tricky actually in this case, and he managed to get a very simple formula, which is, I should write it now, I should have write it earlier.
I have a question.
Yeah, please interrupt me whenever you want.
I don't see the difference between the sphere. Don't you get sphere just by fixing the radius?
What do you mean sphere?
If everything is on a segment, so
yeah.
You can move this around and...
Yeah, if you look at the last point, I mean, you can do everything, but you're looking at also all the individual points. I mean, what they describe in Rn. If you look at the vector of points, what is the possibility for the whole vectors? what you mean if you look at all possible positions of all xi at the same time, that will describe a sphere. But if you look at x1 cannot be at can be at most at distance 1 from 0.
Is xi a point in R or?
No. So I'm sorry. Here it's just the heights of the different points. Okay, it's not the points themselves. So I should have represented as two-dimensional. In fact, we don't, because the rotational symmetry we can integrate on the rotational. It's not really a problem. Okay, so you just look at what possible heights are. Maybe I should have put hi. It's more obvious in this case. But okay, what are the possible heights of the different points? Okay. So this Pn is a volume, and it turns out that I will write it later. Volume of Pn is equal to 2n minus 1. Oh, thank you. 2n minus 1 times 2n minus 3. So these are the double factorials, okay, divided by normal factorials. So for me and for most enumerative combinatorialists, when you see such a formula, you like to prove it bijectively, or at least find some more combinatorial methods than the ones that Bertrand Duplantier used in the first place. So because you cannot really see why these numbers appear, and you like to understand why.
I have a question. So you call, why is it a polytope? What is a polytope?
So polytope, it's the an intersection of half spaces of.
A convex.
Yeah. So it's just intersection. So you have inequalities here. Okay. So they all describe. So these are two half space actually. If you okay, and it's bounded. It has to be bounded to be a polytope. I mean, in the usual definition. Okay, and this is easy bound.
So that's indeed that's definition of the polytope.
Yeah.
That's indeed definition.
So when you have a polytope, it has a certain volume, normal volume in Rn, Lebesgue measure, if you will. And just actually this example is wrong. Oh, it starts badly, but so I will do an example for n equals 2. I don't know where I should draw it so that everyone can see, maybe here. So, okay. So x1 and x2 have to be positive, so it will be in this quarter plane. Okay. Then there's just one condition. No, excuse me. So, okay. So you have x1 minus x0, which has to be smaller than 1. x0 is 0, so it's x1 is smaller than 1, which means, so if this is 1, 1, 2, I have a line here, and it will be on this side of the line. Okay, so already it's in this region. And then another equality is x2 minus x1 is smaller than 1. In absolute value, so one of these two is x2 minus x1 equals minus 1 would be here. So it doesn't bring anything new because we're already in this region. But the other one is here. Okay, and this has to be on this side of the. So in the end, you don't have what is pictured there. Actually, this comes from another, just a change of coordinates. Okay, it's just if you put yi is the sum of the xi, something like this. So you have this, okay, this polytope here. And you can see that the formula is valid in this case because it's 3/2, which is exactly the volume. But we'd like to prove it in general, not just for n equals 2. So how will we do this? So to give the idea, we'll try to find some subpolytopes inside and to decompose this polytope into smaller, very small polytopes inside, which have all the same volume, which will be 1 over n factorial. And we'd like to count how many subpolytopes there are, and we like to prove that they are exactly this number of subpolytopes. So we'll determine that they are 2n minus 1 times 2n minus 3, etc. subpolytopes, each of them having volume n factorial, 1 over n factorial. So this is the definition of the what I will call elementary polytope. So you have to take h a point with integer coordinates, and sigma so a permutation of doesn't work so well, of the integers 1 to n. So given h and sigma, you define the elementary superpolytopes as you want the points to be between hi and hi plus 1. Okay, so this gives, in fact, if you think about it, a sort of little cube which with one vertex is hi. So for instance, if make an example, if h equal 2, 3, okay, n equals 2, okay, this will mean that if you have 2, 3, h is here, and you want the coordinate, already you want these conditions, so y2 has to be between 2 and 3. So this is, sorry, this is y1 and y2 now. So between 2 and 3, y2 must be here, and y3 must be here, between 3 and 4. Okay? So this will give already this little two-dimensional cube. Okay, this is the first condition, and then you want to subdivide this cube, in fact, into n according to the permutation. So this means that so epsilon is the fractional part. Okay, so it's a number minus its integer part. Okay, the numbers after the comma, whatever, after the point, depends on country. So it's if you want the number between 0 and 1, such that t minus epsilon of t is an integer, and you want this condition on the ordering of the fractional parts of the point. But first thing you notice actually is that EH sigma is just a translate of E0 sigma. Okay, because H is just a vector to translate everything by the vector H. So an example, so I can do everything for H equals 0, and it's if you want the same result for any H, you just translate the subpolytope that you obtain. For H equals 0, if you take, very simple, sigma equals 2, 1. So I put the permutations in one-line notation. So this is sigma of 1 and sigma of 2. Okay. So what should this be? H equals 0, sigma equals 2, 1. So as we said, H equals 0, which means that we will lie in this little cube, because 0, 0 is here. It has to be between 0 and 1, between 0 and 1. And then the condition, this condition is that the fractional part of y2, okay, sigma inverse of 1 equals 2, and sigma inverse of 2 equals 1. It means that the fractional part of y2 has to be smaller than the fractional part of y1. So here we are already between 0 and 1. So it means that y2 has to be smaller than y1. So it means that you subdivide here, and y2 smaller than y1. It's here. Is it true? Yeah. So this is an elementary superpolytope. So it's easy to see that these conditions, if you take all sigmas given H, they will subdivide a certain cube into n factorial subpolytopes. Okay, they will give dissection, decomposition of it. All of them will have the same volume because it's just a change of coordinates, and this volume has to be the same, has to be 1 over n factorial, so that the volumes add up to 1 at the end. Okay, so all these subpolytopes have the same volume, 1 over n factorial. And now what we want is to find which of these subpolytope, which can be anywhere in the space, which among them are in our the polytope that we want to compute, which is whose volume we want to compute, which is Pn. So what are the conditions on H and sigma so that the elementary polytope EH sigma lies in Pn? Okay. This is very, I will not go into detail, it's just simple calculation, very elementary. So the result is here. It's in, everyone can see? Yeah. It's included in Pn if and only if H1 equals 0, all the HRs are positive, and you have this strange condition that's over here, that the difference between Hi and Hi minus 1 is either 0 or sine of the difference between sigma I minus 1 minus sigma I. Sine is just if this quantity is positive, sine is 1, and if this quantity is negative, sine is minus 1. I should have written it somewhere. Okay, so it's this difference can be 0, 1, or minus 1, and 1 or minus 1 is dictated by the value of this the difference between sigma I minus 1 and sigma I.
So what is the difference of permutation?
No, it's just a value of permutation. So it's sigma of I minus 1. Okay, I always write permutations like this: sigma 1, sigma 2, sigma n, like a word where sigma I is just sigma of I. Well, you have to believe me on this, but you can also check it. It's 5-minute check. It's really easy to check. So it's included, but it could happen that we have some polytopes that are partly inside Pn and partly outside, but we designed this polytope so that this does not happen, so that they're either completely inside included, or the interiors of talking about topological interior, okay, are disjoint, so that the other ones do not take part in the computation of the volume. So we only have to take care of these subpolytopes. And now what we want to know is how many H sigma, how many couples like this are there, so that we can compute the original polytope. And to do this, we'll what is written here? So H sigma will represent this these pairs as some path. Okay. So it's very easy to do. You take all the Hi sigma I, so you take coordinates by coordinates, and you present them as points I minus 1 Hi. So if I take any H and any sigma, okay, if I take H equals 1, 2, 5, and sigma equals 3, 1, 2, I will have, okay. What I mean, so I will just start at minus 1, okay. This will be the different heights of the point, and then when I go from right to left, so this will be 1 point for minus 1, for the abscissa, for the x coordinate 0. For 1, I will have 2, another point, and 5 will be somewhere around here. I will draw a path like this, and sigma will just label the points with. So this, I mean, this works for any H and sigma. Now we want to see what kind of path. So I call this a path. Okay, it's standard combinatorial terminology. What are the paths that you obtain when you have a good H sigma, one that corresponds to a subpolytope that is included in big polytope? Okay, so this is what you obtain, and it's really easy to see. So positive paths just mean that the different heights are positive. So here the Pi that you see actually are the. It's a bit messy, I'm sorry. Pi in fact must be something like Hi plus 1 minus Hi are the differences in heights. Okay, so if you have a path like this, when I say alphabet minus 0, 1 means that Pi can take the value minus 1, 0 or 1. And so these Pi's will describe the steps. So Pi equals 1 will describe an up steps. Okay, just Pi equals 0. So that's what I mean when it describes the difference in heights between Hi plus 1 minus Hi minus 1. something like this. So the condition, but I will draw one now, so it will be much easier. So positive path means that it stays above this axis, the horizontal axis. Okay. The fact that pi belongs either to -1, 0, or 1 just means that the paths are just these three ones. Okay, you can go up one step, you can stay level, or you can go down just one step. So this is the only step that we are allowed to take. And now so the points are labeled, but you cannot choose any label. You know this weird condition of the hi minus h minus 1 translate here in the fact that if you have a down step, okay, pi equals -1, means that the value on top has to be smaller than the value below. So first, I'm very sorry for this choice because I should have. We can do all the same with choosing the top value to be bigger than the smaller, than the lower value. It would make things easier, but I'm sorry. So just remember that if you have a down step, the value here is smaller than the value here, and it's actually the same if you have an up step. This condition here means that the value on top is smaller than the value below. When you have an horizontal step, you can have in this order or in this order, meaning the first one, or there's no order, no condition on the order. Okay? So I don't think these paths have appeared anywhere before in the combinatorics literature. So because now we have to count them. Okay? It's supposed to be, if you remember, it's supposed to be these numbers, because each of these paths corresponds to a subpolytope. Each of the subpolytopes has volume 1 over n factorial. So the paths like this of length n, there must be exactly this number. So that was, it was most difficult part to try to find why there are these numbers. The first step actually is not to consider this path, but a closely related class of paths that are called Motzkin paths here. Oh, sorry, I'm going to give some example to see that this formula is correct. You can check. If n equals 1, you have just one path. Just you stay at the. If you have n equals 2, you can either stay label, and then all possible permutations are possible, or you do an up step, and then this one has to be smaller, bigger than this one. You cannot do a down step, okay, because you have to stay above the horizontal axis. And then you can check that for n equals 3, you have these 6 ones where you have no condition, then these 3 ones, etc. So 1, 3, 3 times 5, 15, it works, but it will prove that it works in general. Okay? It was, we thought it would be quite easy to find a bidirectional with matchings, but actually it's quite complicated with matchings. Matchings are the objects that I'll talk about later. But to try to find bijective proof that there are these numbers was not so easy in the end. The bijection in the end is quite complicated. So I will talk mostly about this well-labeled Motzkin path. They are nearly the same as the other ones, except that the shape is different. So the condition 2 is exactly the same, okay? The label on top has to be smaller than the label just below, okay? But this condition just means that it has to stay positive, except the last step that has to go from height 1 to height -1. So these are called also extended Motzkin paths. Usually what we call a Motzkin path, it ends on the horizontal axis. But here, it turns out that the good thing to do is to consider the ones that have one extra step going down. And it's not equivalent to the normal Motzkin path because of these labeling conditions that are a problem. So I will focus mainly in this talk on this path and trying to find bijective proof of the enumeration of this path. And at the end, I will come back to the positive path and say why we can use this path to count the previous ones. So everyone understood what these paths are exactly? Because that's all we need for the rest. Okay, I will not come back to the polytope or whatever. So well labeled, okay, stays above the axis, and one extra step at the end to go to height -1. So I'll call M the class of Motzkin paths, P the class of positive paths. So that's what I said, that it's easier to consider first the class of Motzkin paths, and then I will generalize to, in the end, I will go quickly how to go to positive paths, the original ones. So to do bijective proofs, we have to find something that is counted by this quantity. And in combinatorics, normal object, let's say, are what I call a matching, which are called also perfect matchings in general. So it's just a partition of 2n with blocks of size 2, or an involution on the points from 1 to 2n without fixed points. So an example, you can draw them as just pairs. So if you have, so this is for n equals 3, so you have twice the number of points, and you want to join 2 by 2, just join 2 by 2 the different points. So you could join 1 to 4, 3 to 5. I will draw them like this most of the time, okay? So we just join 2 by 2, and the order in each case is not important, okay? Just don't put any order. So why are there these numbers of matchings? It's very traditional. You try to find first what could be in the same pair. I mean, what could be joined to 1. You have 2n minus 1 choices, okay? So you first draw this one. Then there are some points remaining. You take the first one remaining, and you try to see to what it could be joined. And yet, by simple computation, there are 2n minus 3 points remaining. You do this over and again. You find the formula in the end. Okay. So the goal now for nearly the rest of the talk is to find a bijection between this Motzkin, the class of path and matching, because it turns out that the Motzkin path, the second family, is also counted by some matchings. We will also have this formula for the other family. I mean, at a slightly shifted. Which I mean, so this is the main theorem, that there will be bijection between the class of positive path of length n, and also the class of Motzkin path now of length n plus 1, so we have to take one more point, and the matchings of 2 on 2n. Okay. So this proves immediately that the enumeration, okay, that I talked about, and the result for positive paths that I dealt with in the introduction, the volume of the polytope n will be equal to this. So 2n minus 1 double factorial is normal way to it's a short way to write down this expression, okay, because you take one out of 2 integers each time. So I will now go through the bijections. So they will use some, it's a composition actually of 2 bijections, and I don't see any good way to go directly to matchings. So I will go first to certain class of trees that I will define soon, and then from these trees to the matchings. So the first bijection is really recursive. So we will describe the recursive decomposition of our path, and then see that the class of trees that I will define obeys the same recursive decomposition. So you can define a bijection. Okay. So look at this decomposition. It's one of the main points. So you can decompose the path and see there are 3 cases. Either it begins. So I'm talking about Motzkin paths. Okay, so the ones that are positive and at the end make an extra step to go to height -1. So either you start with a -1 step and then it's done. It means that it's only a length 2 path. Or you start with a horizontal step, and then in the end what you do is also a Motzkin path, except that you have to relabel sometime. It's not really important. Or the third case, the most interesting, you start doing an up step. So then you know that you will eventually go down to height -1. Means that you will do some paths, some steps above the height 1, but at one point you will have to go down to height 0. Okay, so this decomposition means that I cut at the first step that goes from height 1 to height 0. Okay, the first time that you go back to the horizontal axis, then you cut. So what do you have? The path is cut in two parts, this part and this part. This part is quite easy. It's also a Motzkin path, okay, except up to relabeling things, okay. But this one, if you do a vertical symmetry of this path, meaning if you read it this way, from right to left, then if you look at the conditions, it's also exactly a Motzkin path. So this is just the class of reflected Motzkin path, which is enumerated by the same numbers, etc. Okay. So in fact, this is also a Motzkin path up to this symmetry. So we managed to break down, if you want, a Motzkin path in two smaller Motzkin paths. So really, if you look at this, you have a complete recursive decomposition of this path. If some combinatorialists are not interested in bijections, so when they have this kind of symbolic equations, they write down equations on the generating functions of the thing. So you can do this, and it works very fine here. So generating functions, I don't know if anyone is familiar with it. It's just the exponential generating function. It's just this power series where the coefficient of z over n factorial is the number of Motzkin paths of length n. Okay. So just the coefficients are the numbers we are looking for. And so if you're not familiar with it, maybe it's a bit complicated to understand, but it's really automatic to go from this kind of decomposition to decompositions on to equations on the corresponding generating functions. Because this is in fact the generating function of this class reduced to one single path. This corresponds to multiplying by z. Okay, I will not go to my. And just here, usually when you break down in two things, you just have the squares. Okay, it's mz. This is counted by m. This is counted by m. So you would have m squared. But here you have to be careful that these are labeled. Okay, I ignore this here, but these are labeled, and here the labels are not in any possible order. So this label has to be smaller than this one. So in fact, you just count half of them. If you think about it, it's really, you can group them 2 by 2, or there are many ways to count it. So just half of the possible paths will go here. Okay, so that's why you have to divide by 2. But this is a quadratic equation. You can solve it, and then you can expand it as power series, and you will find that mn plus 1 is 2n minus 1 double factorial. It's really standard calculus, okay, to do this. So you can also, for those people who are familiar with it, do Lagrange inversion formula. If you modify a bit this equation, you can apply Lagrange inversion formula and directly get the coefficients without solving anything, if you want. Okay, but I want to talk about bijections, so I will go. So how much time? I have to hurry a bit. So the trees I consider here are binary trees, rooted, such that the labels are only on the leaves. Okay? So, and they are of size n if there are n leaves. And the labels, maybe, I don't know if you can see, but there are labels 1, 2, 3, okay? Labels from 1 to 10 are only on the leaves. And they are unordered children, meaning that if you exchange this tree and you put it this place, okay, it's the same tree. I mean, the order of the children doesn't matter. Okay? I mean, if you put 6 here and 3 here, it's the same tree. Okay, it's up to order of the children. And now this is maybe there is a bijection first between the Motzkin path and these trees. So actually, I found this in Stanley's book more or less because I didn't know how to find it, and I found a recursive decomposition of these trees. I mean, the generating equation, it's exactly the same as I did. So you could define directly the bijection. And from this, I could pass to matchings. But before hitting upon it in Stanley's book, I was completely lost. I had no idea how to do it. So the bijection is really easy because a tree, it's either a tree with, a non-trivial tree. I don't consider the tree which has just one root. Either it has 2 leaves as children, or it has 1 leaf and a non-trivial tree, or it has two non-trivial subtrees, meaning not reduced to the root. And this corresponds, if you can recursively see that it's exactly the same as this, because this you will attach to this one. So the path of this form we attach to this by putting the label here, and recursively attach this subtree to this path. Okay? Clear? And it's about the same here. You have two Motzkin paths, sort of, as I described, and you can attach them recursively to the two subtrees of this. So I'll maybe give a... still have some time. So, or maybe I can do it here. So what I mean, so if you want to do the bijection now, if you want to do a complete example, you have this path, Motzkin path, sorry. So what kind of path it is? You know, remember there are three kinds according to the first step. So this starts by up step, so we have to cut it at the first time where it goes back to level 0. So it's just here, okay? So this will give one Motzkin path and another Motzkin path if you read it backwards, okay? 3, 6 is also a Motzkin path up to relabel. And as I said, this will become this subtree, and this, the big one, will become the other subtree, okay? So if you want to deal with this one first, this is a base case, if you want, so it will just become this subtree, okay? When you have just a down step, because you have to read this, it becomes a tree with a root with two leaves, 3 and 6, okay? But here, for instance, now you consider this one. It's also type 3. I mean, it starts with an up step, so you have to cut it here. First time it comes back to 0, okay? And then you have, this will correspond to a subtree, and this also. And you can see it here. You have one subtree corresponding to this, and one subtree corresponding to the big one. Just the last step. I mean, you can understand, but the case of the horizontal step, okay? If you start with the horizontal step, you will cut here. You will have 7 on one side, which will be a leaf, and 4, 9 on the other side. So here is a leaf 7, and here are 4 and 9. Okay? So this, you have to believe me, it's a real bijection. It's very easy to come back. Okay? You follow the same recursive decomposition to come back. So now we want to go from these trees to matchings, because that's what we know how to count, because these trees are not obviously counted by this. Okay? So this was also in Stanley's book, actually, bijection due to William Chen. And how does it go? I will show an example. I think it's much easier. Directly the example. So you want to label all, so you have labels on the leaves, and first you want to label, using these labels on the leaves, you want to label all internal vertices, okay? Except the root. You don't need to label the root. And you will label them by n plus 1, n plus 2, and in this order. So here n equals 10. So you will put the labels 11, 12, 13, up to 18 if you count, okay? And you want to attach these labels 11 to 18 to the internal vertices now, okay? So how do you do this? The recipe is, first you look, so you see the circle vertices. They are the unlabeled vertices such that their two children are labeled. Okay? If there are no mistakes. There can be mistakes in this. Please tell me. But this has two labeled children, etc. And the other ones have either 0 or 2 of their children that are unlabeled. Okay? And then you have to pick one among them to which you will attach the first unused label, which is 11. And you choose, among these 4 vertices, you will choose the one that has the smallest child, the child with the smallest label. Okay, the labels of the child is 4, 9, 2, 8, 5, 10, 6, 3. So the smallest is 2 among these labels. You all agree on this? So this is the one that you would choose to be labeled by 11. Okay? And then you do the same. You just do the same procedure recursively. You select the vertices with 2 labeled children, which can be leaves, or because now you start labeling everyone. So labels are not only on leaves. Okay, so these are the 3 ones with 2 labeled children. You find that the smallest child among these is 3. So you will attach 12, the next one, to this vertex. Then you have these two, okay, 10, 5 and 4, 9 are the children, 4 is the smallest, so 13 will be attached to this vertex. The same, 5, 10, 7, 13, smallest is 5, so 14, okay, the next unused integer will be attached to this, etc. Okay, so this way you can label, I mean, it's easy that you can label all vertices. But this is nice, but we want a matching. Actually, it's very easy to come out with a matching out of this. You would just put together all labels that correspond to children of the same parent, okay, siblings, if you want. For instance, 5 and 10 are children of 14, so they will go together. Or 2 and 8 are children of this one. 14 and 11 are children of this one. So we join them, and in the end, you see, 1 and 16 are children of this one, etc. So this is how to obtain, you see, this is really a matching. If you can draw it another way, it means that 5 would be joined to 10, etc., 2 and 8, etc. This is a bijection. As I said, it's not due to me, it's due to bitchain. It's actually trickier to see that it's a bijection to come back. If I give you a matching, can you reconstruct the tree from it? It's not obvious, but it works. So now we have finally the bijection between Motzkin path and matchings. Positive paths, so I don't have time to, I mean, maybe in the question session I will be able. But there's also decomposition for positive path, okay, recursive decomposition. That it's a bit trickier because you have more cases when the first step is high. I mean, I want to finish on time, so maybe I can come back on this if you want. And the bijection, now we will go through trees again, but we will not consider just trees, but marked trees, meaning trees where you distinguish one of the vertices. Well, if you count in labeled trees, there are 2 n-1 vertices in total. There are n leaves and n-1 internal vertices. So it's easy to see that since there are 2n, okay, whatever. So there's a bijection, also recursive, between this positive paths and marked trees. And if you have marked trees, using Bilchen's bijection and modifying it just a bit, you can find a bijection between marked trees and matchings on 2n. Okay, maybe you didn't notice before, but this didn't go up to 2n, just to 2n-2. Okay, there's a little shift for Motzkin path. And now if you consider marked trees, so imagine, let's say 6 would be marked, then you could do a bijection with the matchings on 20 points, okay, 2n. So summary of the bijections, it's just you have Motzkin paths, then you have trees and then matchings. If you have positive paths, you have marked trees, so one of the vertices marked. And there is I I didn't describe this, but there's a way to go to matchings on 2n points now. So this proves eventually the volume of the polytope, okay, because we have 2n-1 double factorial positive paths, etc., corresponding to subpolytopes, each of them having volume 1 over n factorial. So a little refinement is if you want to count Motzkin paths or positive paths, I can do the same, with k horizontal steps. Okay? And this is, can I go 5 minutes? 5 minutes more? Okay.
5 minutes before
What?
your talk.
Oh, okay. Just in the recursive decomposition, I will just, sorry. It's easy to see that in a recursive decomposition, you have a horizontal step. It's transformed in a leaf, okay, such that the sibling of this leaf is not a leaf, okay. This is the case. Here, leaves have as brother, if you want, another leaf. And here is the only case where you have a leaf such that its brother is not a leaf, it's sibling, okay. That's what I call a single leaf, okay. And in general, horizontal steps correspond bijectively to this kind of leaves. But if you look at the next bijection, single leaves, they have labels between 1 and n, okay? And the fact that they are single means that their brother is an internal node, so that its label will be more than n. So it will be between n plus 1 and 2n minus 2, okay? This means that horizontal steps will correspond to pairs in the matchings, such that one of the integers is smaller than n, smaller or equal to n, and the other one is greater than n. Okay, so that's what I had written here. Okay, horizontal steps become single leaves, and they correspond to pairs one between n. And this is very elementary to count. You can count them, and they are exactly so. The number of well-labeled Motzkin paths of size n avec k horizontal steps is 0 if n minus k is odd, so it's very easy to, okay, it works. And otherwise, you just count these matchings, and this is given by this expression, okay? I can show you if you want, but it's quite easy to compute. You can do the same with positive paths. It's a bit more complicated. You have to modify the notion of single leaves. There's a slight modification, okay? But it was the same, and you have very similar expression for the number of paths with a given number of horizontal steps. So in the end, if you have no horizontal step, you realize that the permutation completely determines the path. Because if I give you, if I take any permutation, let's say 3, 1, 4, 2, 5, and you want to see what path, I mean positive, Motzkin, any kind of well-labeled path would give rise to this permutation. It's 3 and 1 are in this order, so you have to do the first step this way. I mean, I'm talking about paths that have no horizontal steps now, okay? K equals 0. And then 4 has to be below because of this order, and the permutation completely determines the path, okay? This is quite exactly 4, 2, 5. Okay, so now we want to count the permutations such that the corresponding path with no horizontal steps is a Motzkin path, for example, or such that it's a well-labeled positive path. Okay, and this is related to the notion of descents and ascents in a permutation. A descent is when you have a position I, such that position I, so I equals 3 here, such that the next value of the permutation is smaller, so it goes down. Okay, unfortunately it goes up here, so it's really a bad choice to this thing, but whatever. So, and the up-down sequence, in fact, don't really have to read this. It's just the path that it makes. I mean, up to symmetry, the up-down sequence of permutation would be the unlabeled, if you want, path that you obtain when you see the sequence of ascents and descents. Okay, you can. If you have an ascent, you go up. No, you go down. If you have a descent, you go up. Etc. So, what permutations? How many permutations are there so that the corresponding up-down sequence is positive? It's a very natural question because it has been quite studied, this up-down sequence of permutations. But usually it's studied if you fix a path, a single path, and you try to find how many permutations have this path as up-down sequence. Here I consider a whole family of paths, the ones that are positive or the ones that are Motzkin. Okay, so I'll count them all at the same time. And you just apply the formulas that I had before for k equals 0 because it just corresponds to path, to well-labeled Motzkin paths or positive paths that have no horizontal steps. So the formulas are very simple. The number of permutations of size n having a positive up-down sequence, so that if you draw this up-down sequence, like this one, for instance, it stays above the axis. Okay. This is part of things that are counted by n minus 2 double factorial squared because it's even. There's a little difference if n is odd, n is even, and you have also formulas for the well-labeled Motzkin paths, which are Dick paths because there are no horizontal steps. Okay, for people who know what Dick paths are, it's no horizontal steps. So you have very simple formula for these classes of permutations. And I'll stop here. And thanks for your attention.
Questions or comments?